Okay, so I'm just going to start with a brief introduction to Habitable Worlds Observatory. I think a lot of people here are very familiar with it, so I won't spend too much time on this. These are stock slides stolen from the Habitable Worlds Observatory kind of standard slide deck. So what is the Habitable Worlds Observatory? Well, it's NASA's next flagship mission, astrophysics mission after the Roman Space Telescope. It was recommended by the Astro 2020 Decadal Survey, sort of. I can talk about what I mean by sort of in the questions if you want to know the answer to that. It is the first telescope specifically designed to search for life on planets outside the solar system using the direct imaging method. It's notionally a large aperture, 6-meter twiddle, UV optical near-infrared space observatory that is very, very stable, is capable of high contrast imaging, and that platform also enables a lot of transformative astrophysics with the right instrumentation, which I'll talk about. So the preliminary specs and candidate instruments are derived largely from the LUVOIR final report and the HABEX final report. LUVOIR B and HWO notionally look fairly similar to each other in terms of aperture and sort of what instruments are going to be on, or likely going to be on the Habitable Worlds Observatory. So again, the telescope is roughly 6-meter diameter. That's, if you're thinking about a segmented telescope, that's the inner inscribed diameter. The bandpass is somewhere between 100 nanometers and 2.5 microns. There's going to be at least 3 instruments, coronagraph, which is going to do the high contrast imaging, the high resolution imager, which is going to be kind of the focus of this particular application that I'm going to talk about today, and a UV multi-object spectrograph. There will be a 4th instrument, maybe, to be defined, or there at least be room for a 4th instrument, and there's also going to be 2 guide cameras, and some of the science I'm going to talk about may be possible with the guide cameras. That's again TBD. So the main exoplanet goal of HWO is to directly image an Earth-like planet and take its spectrum and look for signatures of habitability and potentially life. So this is a simulation of what our solar system might look like, taken with the HWO. You can see the star is behind the coronagraph. You can see Earth, you can see Venus, Saturn, and Jupiter. And in principle, we could get spectra of all of these planets. And when we often focus on looking for habitable planets, and so this is a simulated spectrum of what a nearby Earth might look like, modern-day Earth. And you can see the spectrum going from the near UV all the way to the near infrared. And I think the thing to point out here is the y-axis is in units of 10 to the minus 10 in terms of the flux, planet-star flux ratio. That's an incredibly small number and drives the telescope stability, achieving that kind of contrast. And for reference, I forgot to mention in the previous slide, an Earth around a nearby sun-like star is about 30th magnitude in V. The star itself is a 50th magnitude in V for a star at 10 parsecs. So you can see lots of features here. You can see Rayleigh scattering, which is indicative of an atmosphere, the water vapor lines, the oxygen and ozone, and so these are all indicators of potentially habitable conditions and maybe even life in exoplanet. So interpreting a planet spectrum, we hope to get these planet spectra, but interpreting them will require understanding the context in which this planet spectrum is detected. So things we will want to know about the planet and the star and the system. We want to know the planet mass, radius, and orbit. So we know the stellar insolation, for example, and the stellar surface gravity of the planet. We want to know stellar properties, mass, luminosity, temperature, abundances of the planet, high energy emission, and then we want to understand the planetary systems, what other planets might be in the system, the age of the star, and its birth environment. And all of these will help us to interpret the spectra that we get. Now, you know, one of the main goals, obviously, is to look for Earth-like planets around nearby sun-like stars. But it also enables us to be able to detect and characterize hundreds of other types of planets that have larger flux ratios than the Earth to the Sun. And so this is a simulation by Chris Stark that's showing the yield of the LUVOIR B design, which is going to be roughly comparable to HWO. For different kinds of planets. So we have sort of Earths, mini Neptunes, and Jupiters, and we have sort of hot, warm, and cold planets, all of which are capable of being detected and characterized with HWO. All the way to the left is the actual Earth analogs you see, and there's roughly 25 is the requirement from the Astro 2020 Decadal Survey. So all of these will come for free to some extent. And we can get spectra of all of them. So here's some simulated spectra of what these planets might look like. So we have Jupiter, Jupiter analog, a Jupiter at 2 AU, Neptune at 2 AU, Jupiter at 0.8 AU, and a Venus-like planet. And we can see lots of great features here, lots of water features, methane features, et cetera, depending on the planet. And so we can measure the abundances of the planets and characterize their atmospheres. And so we can start to do comparative exoplanetology on our nearest neighbors. And that's very exciting. And we can start looking for things that will tell us about how planets form and maybe how they evolve and over time. So, for example, one game that's been played a lot recently for transiting planets is to go and take spectra using transmission spectroscopy or eclipse mapping eclipse spectroscopy to measure the abundances of different features of transiting planets and then compute the planet abundance relative to the stellar abundance, which is what's shown on the y-axis, as a function of the planet mass. In our solar system, you can see in our solar system there's a very well-defined trend, kind of shown by this orange line, where the less massive giant planets, Uranus and Neptune, have higher relative metallicities compared to the star than Jupiter and Saturn do, and it's a sort of monotonic function of mass. This is likely a signature of core accretion, the formation scenario of these planets, and so this is telling us something about how they form. People have tried to do this for transiting planets. I think the results are a little harder to interpret, and the measurements are quite challenging. But perhaps, you know, if you look at this squint, you'll see that there's maybe some sort of trend there as well if you measure the water abundance as a function of planet mass. Again, telling us likely something about how these planets form. We'd love to be able to do this for the planets that are detected and characterized with HWO, but in order to do that, we need the masses of the planets. Okay. So, so how do we get? So I'm going to focus in this talk on how we measure the planet mass. I'll talk a little bit about the planet orbit, and then I'll also talk about how we get the stellar mass as well, which kind of comes for free with the high precision astrometry. Okay, so how do we measure? So there's an interplay between detecting nearby planets with direct imaging, astrometry, and radial velocity, in the sense that some of these these methods of measuring masses, astrometry, and radial velocity are complementary to the direct imaging in different ways. So one way to look at this is to plot the contrast ratio of nearby of an Earth planet in the habitable zone of nearby stars. So you can plot the contrast ratio as a function of the astrometric signal that you get from the reflex motion of the planet as it orbits the star as it orbits the center of mass of the planet-star system. So what you see is that the size of the circles are proportional to the angular separation between the planet and the star, the maximum angular separation, and then the color coding is proportional to the radial velocity amplitude of the planet. So what you see is that as you go to, see there's several things to note. There's a clear trend with contrast ratio and astrometric signal. This is not a surprise, but as you go to larger, planets that have larger astrometric signal, their contrast ratio goes down, and that's because they're generally orbiting stars that are more massive, and that planets are therefore farther away to be in the habitable zone. That means also that the radial velocity signals are low, less than a meter per second. As you go to lower mass stars, the contrast ratio goes up, but the angular separation of the planet from the star goes down, but the radial velocity amplitude goes up. So you get this natural division between planets orbiting high mass stars, habitable planets orbiting high mass stars, and habitable planets orbiting low mass stars. Those orbiting high mass stars have larger astrometric signals, but larger angular separations, but smaller contrast. Those orbiting low mass stars have larger contrast, smaller angular separation, larger radial velocity, semi-amplitude. And so this kind of naturally divides the parameter space into searching for habitable planets around low mass stars and searching for habitable planets around high mass stars. And the so-called small star opportunity, which is the kind of low-hanging fruit that we have now of trying to detect and characterize Earth-like planets around low mass stars, is what we're spending a lot of our time with JWST now doing, because these planets are easy to detect with transits and radial velocity, and then we can go and characterize them with JWST. For the habitable planets orbiting high mass stars, that's out of reach. So we have to use direct imaging in that case. So ground-based, low contrast, small semi-major axis, space-based, high contrast to large. Okay, and there's alpha set A and B, which is kind of, in some sense, the ideal system for doing direct imaging, except for the fact that it happens to be in a binary, which makes direct imaging more complicated. Okay, the other way to look at this is the astrometric signal as a function of the period. And so of course, these are related. The larger the period, the larger the astrometric signal. This is again for Earth analogs around nearby stars. And so as you go to smaller periods, as you go to lower mass stars or lower effective temperature stars, the habitable zone gets closer, the period gets shorter, the astrometric signal goes down. Conversely, if you go to higher mass stars, the astrometric signal gets bigger and the period gets bigger. So again, you have this natural division between habitable planets around low mass stars and habitable planets high mass or high temperature. Okay. And so if we now focus on the two ways in which we can measure masses of nearby Earth-like planets around nearby stars, which are radial velocity and astrometry, then this plot by Eric Mamajek shows the signals in astrometry and radial velocity, again, of an Earth analog around nearby stars. This is for the LUVOIR HABEX target list. And again, this is a one Earth mass planet and located at equivalent of 1 AU, or a stellar insolation equal to that of the Earth. And so all of the targets cluster around this small area here in this kind of very scary region of parameter space. Note the units here are in centimeters per second, log centimeters per second on the x-axis, and then microarc seconds on the y-axis. And so for an Earth analog, you have around a sun-like star, which is sort of located here. You have an amplitude of about 8 centimeters per second, and an astrometric amplitude of about 0.3 microarc seconds. These lines show various state-of-the-art precisions in astrometry and radial velocity. I'll talk a little bit more about radial velocity here in a second. But right now, we're just barely able to get below about half a meter per second in radial velocity. And astrometry, Gaia, state-of-the-art, at the end of mission will be of order tens or 30 microarcsecond for the nearest sun-like bright stars. So we're orders of magnitude away from being able to detect Earth-like planets around nearby sun-like stars with either radial velocity or astrometry. Okay, so just to put it into numbers, the Earth around a sun-like star at 1 AU at a distance of 10 parsecs gives you a 0.3 microarcsecond astrometric amplitude, and so that's a small number. It's pretty scary. We can ask how that scales for different mass stars, assuming the planets are in the habitable zone. If we assume that the luminosity of the star scales as the mass of the star to the fourth power, which is roughly true for sun-like stars, then the signal increases as the mass squared. Sorry, I dropped a unit here. And so you do better for higher mass stars. So habitable zone planets are easier to detect with astrometry for higher mass stars. Conversely, with radial velocity, the signal scales as the mass of the star to the -3/2 power. So you do better for lower mass stars, which is what those plots were showing. And the semi-amplitude for an Earth analog around a sun-like star is about. Okay, so again, using astrometry or radial velocity, you have this sort of natural division between habitable planets around low mass stars and high mass stars. Okay, so I'll spend a little bit of time talking about radial velocity, mainly as a way of motivating why we want to try to do astrometry with HWO to detect, measure masses of the directly imaged planets. So with radial velocity, we have three sources of noise that we have to contend with. One is just photon noise. So, you know, how do you measure precise radial velocities? Well, you take very high resolution spectra, so you're resolving all the spectral lines. Each spectral line you can centroid to, you know, many tens of meters per second, but you have many spectral lines, thousands of spectral lines, and so you can aggregate all of those and beat down your photon noise precision using all your spectral lines. But you know, we're talking about 100 resolutions of 60,000 or 100,000 that you need in optical spectra in order to do this. And that means that even for 5th magnitude stars, which is typically what we're talking about, you require exposure times that are relatively long on relatively large aperture telescopes. Fortunate thing is you can do this from the ground. There's not much that going to space. Well, you can do this from the ground. Going to space does buy you something, but I don't have time to go into that. The second thing is your instrument actually has to deliver the stability you need to measure these very small radial velocity shifts. And so basically what you need to know is if you have light falling on one place of your detector, you have to know exactly what wavelength that corresponds to. And so there's all sorts of things that can change the wavelength of the photon that lands on your detector, where that corresponds to on your detector. Things like just thermal flexure of the telescope, other things like that can cause these radial velocity effective drifts that you have to take out. Modern spectrographs designed purposely for radial velocity can have error budgets and the stability of sort of 20 centimeters per second. So we're not quite where we need to be, but in principle, we're not far off. So the photon noise and the stability of the instrument is generally not considered to be the high bar in detecting Earth-like planets around sun-like stars. Rather, it's the intrinsic stellar activity. So with radial velocity, what you want to measure is you want to measure a coherent Doppler shift of all your spectral lines such that they move back and forth without changing their shape. But stellar activity can cause the line shapes to change in a way that if you're just measuring centroids of lines can look like a radial velocity shift. And there's all sorts of effects, which are kind of some of which are listed on the right here on the star, which can cause these kinds of anomalous Doppler shifts or these apparent Doppler shifts due to stellar activity. So things like spots are one that's very familiar, but when you start getting down to tens of centimeters per second or 10 centimeters per second, things that you might not even realize, physics that you might not even realize are happening on stars, like flows from the equator to the pole, can actually cause anomalous Doppler shift portions. And so all of these have to be accounted for and somehow taken out before you can get the signal of the 10 centimeters per second that occurs over the course of 1 year. And there are lots of people working on this very hard. There's lots of ideas for how to solve the stellar activity problem, but we're a ways off. And even if we can solve the stellar activity problem, then there's always going to be stars that are not amenable to radial velocity. So for example, if you have very active stars, that activity is not going to be at the level of 1 meter per second that you have to take out. It's going to be at the level of tens of meters per second, or even many tens of meters per second, and that's going to be very hard to take out. But a more fundamental limit is just from the fact that hot stars have fewer spectral lines, and the lines that they do have tend to be very rotationally broadened. And so if you plot the typical V sin I of stars as a function of their effective temperature, these are cooler stars, so a sun-like star is right here, then you find that as you go to hotter stars, you get very high V sin I. And the fundamental reason for this is that hot stars have very thin convective envelopes, and therefore don't create a dynamo to generate ordered magnetic fields. And then therefore, because they don't have ordered magnetic fields, they don't spin down over time due to stellar mass loss in the way low mass stars. So they retain their initial relatively fast rotation. And so that broadens the lines, and therefore gives you much less information. It's much harder to centroid a line that's much broader than it is in a line that's nice and sharp and narrow. So this shows a spectra of simulated spectra of two stars that have the same effective temperature. The one on top is rotating at 100 kilometers per second. You can see that the lines are very broad and are all blended together. So hot stars will fundamentally be not amenable to radial velocity measurements, at least down to the level of tens of centimeters per second. So we can look at the LUVOIR target list to get a sense of how many stars are going to be excluded for measuring by radial velocity. This shows the distribution of spectral types to the right. This is from the LUVOIR final report, plots made by Chris Stark. And this shows the luminosity as a function of distance, color-coded by the spectral, by the completeness of the habitable zone, and then shown as the spectral type. And so all of these stars will only be amenable to spectrometry, not be able to do radial velocity, at least at the sub 10 centimeter per second level. Okay. So all that motivates why we want to do astrometry with HWO. Okay, so astrometric detection of planets, very simple, right? Planets don't orbit stars, they orbit the center of mass of the planet-star system. Stars orbit the center of mass. So as the planet orbits, the star wobbles. This plot on the right shows the astrometric shift of the solar system as seen from, I think, 10 parsecs. If you were looking at it face on, and you can see the signals due to Jupiter and Saturn. And then what is actually invisible on this plot is the tiny little signals due to, for example, the Earth, because that's at the 0.3 microarcsecond level. So that's enormously challenging. And just to give you a sense of what we're going to be looking at, I just pulled this figure from an old SIM paper, Space Interferometry Mission, kind of a dirty word these days, but anyway, one of the goals of SIM was to actually measure masses of Earth-like planets around nearby sun-like stars using astrometry, using a very different technique that I'm going to be talking about. But the per epoch astrometric measurement precision is going to be, several microarcseconds, whereas the signal is 0.3 microarcseconds. And you want to be able to measure that signal at 10 sigma. So you have to get to sort of down to systematic levels of 0.03 microarcseconds. So you can't do that with single measurements. You have to do that by aggregating many, many, many measurements. And so this shows the sort of two-dimensional astrometric position of a star with the planet. There's the astrometric orbit. Looks basically undetectable, but if you plot the astrometric shift as a function of right ascension, or sorry, the right ascension shift as a function of time and the declination shift, maybe you can see a little trend there, a little periodic signal. Then you do a periodogram and you see two peaks at roughly 1 year in your periodogram. So we're going to be digging deep into the noise here, and that should be, you should find that alarming. I certainly do. Okay, so the first thing we want to do to see if we can measure the astrometric shift of Earth-like planets around Sun-like stars using an HWO is to just ask what the signal-to-noise is. How many photons do we have? How well can we measure this astrometric? So I'm going to step through some of the scaling arguments here. So the signal-to-noise of some set of n astrometric measurements, and I'm talking about 2D astrometric measurements, is going to be the square root of those number of measurements times some function which depends on the details of the orbit. This is a dimensionless function which depends on the details of the orbit. If it's face-on, this f is just equal to 1, but if it's edge-on, it's equal to 1, the square root of 1 over the square root of 2. It's equal to the square root of 2, and then if you have a eccentricity, then it's more complicated than that. And that you multiply that by the size of the astrometric orbit, which is this alpha, which I showed before here, and then divided by your single measurement astrometric. And so that's the signal-to-noise with which you can detect the astrometric orbit if the period of your observation, if the period of your planet is much less than the total duration of your observation. If you have, if the period of your planet is longer than the duration of your observations, you're just detecting part of the orbit of the planet, and in fact, that signal falls off quadratically as the period of the planet, or the inverse of the quadratically of the period of the planet, and so it becomes very hard to detect planets that have periods longer than the duration of your. So you can think of the sensitivity of astrometry as sort of increasing as you go to larger periods, and then until you get to the duration of your observations, in which case it basically cuts. Now, given that you have a detection, what is your mass measurement uncertainty? That's just 1 over the signal-to-noise, or sorry, 1 over the signal-to-noise. So you get a signal-to-noise of 10 if you have 100 astrometric measurements, each of which has a 0.3 microarcsecond uncertainty in both axes, and that's for an Earth-mass planet around a Sun-like star. Okay, so that's the challenge that we face, 100 measurements with 0.3 microarcsecond uncertainty. Now, as I said, each measurement uncertainty is going to be larger than 0.3 microarcseconds. So how do we get down to that 0.3? And I'll talk about that in a second. So a signal-to-noise of 10 corresponds to roughly 10% mass measurement if the observations are spread uniformly in phase of the duration of the observation. So 10% is probably the goal we want to reach for being able to characterize directly imaged planets. So this is a very simplified treatment, but it does give you a sort of rough sense of the number and quality of measurement. Okay. So what is the astrometric noise uncertainty? So you have two contributions. One is your ability to centroid the position of the star, target star. And then the second is that you're measuring that astrometric shift relative to a set of background reference stars, because you don't know in any absolute sense where a given star, a given position on your detector corresponds to in the sky. Right? You could imagine trying to do this with Gaia reference stars, where you can establish an absolute coordinate system, but the Gaia reference star precision is not good enough to do the kinds of astrometric measurements you need. Those are only going to be at the tens of microarcseconds, where you need like 2 orders of magnitude less to higher precision. So what you do is you measure your position of your target star relative to a set of reference stars. You assume that the astrometric wobble of the reference stars due to parallax on proper motion can be taken out or fit out, and then whatever's left over is the reflex motion of the target star. So your noise is set by your astrometric uncertainty in your target star and your astrometric uncertainty in your reference star. Of course, the astrometric uncertainty in your target star, which is a fifth magnitude star on average, is basically negligible if you can harness all those photons. I'll get to that in a second. So you're really dominated by the uncertainty in the astrometry of the reference stars, and by extension, the number of reference stars, which you can measure the relative astrometry. So this shows the basic scaling. You get about a 2 microarc second astrometric uncertainty in the centroid of a position of a 15th magnitude star with a 300-second exposure and a 6.5 meter telescope, given a diffraction limit at 500 nanometers of 0.0159 arc second. So it goes as the 2 powers of the diameter. You get 1 power just because of the collecting area, and you get 1 power because the larger your diameter, the sharper your PSF is if you're diffraction limited. So that's for 1 reference star. So if you had 30 reference stars and they're uncorrelated in their uncertainties, then you can beat that down by square root of 30, and that'll get you down to the 0.3 microarc second. So you should think that we require sort of 30 reference stars with the magnitude of at least 15th magnitude. And turns out 15th magnitude stars are actually not that common in the sky. So this is a challenge. So how many reference stars are there? Well, okay, it depends on where you're looking. If you're looking out of the galactic plane, then there's fewer reference stars than if you're looking into the galactic plane. And if you're looking out of the galactic plane, what you'll find is the number of reference stars grows more or less as the volume, because you have more or less uniform density of stars in the galactic thin disk. And then once the volume starts to, the distance out to which you're looking at stars starts to reach the scale height of the disk, which is about 200 parsecs, then your number of reference stars will start to, the rate of increase of your number of reference stars will become shallower as you go to larger distances. And that's what you see here. You see that you increase the number of reference stars as sort of in this power law fashion up until you get this break where the typical distance is of order the scale height of the disk. And beyond that, you have a much flatter of the number of reference stars. And so you can fit this with a double power law. This fits quite well. And so you have a bright end slope and a faint end slope, a surface density of stars at the break between these faint and bright end slopes, and then the magnitude of that break. So typically, what you find is that for the bright end slope, this alpha 1, the surface density of stars goes as 10 to the minus 0.4 times the V magnitude. And what does that mean? That means that basically, that's basically what you'd expect if you have a uniform density of stars of a fixed magnitude. So as you increase the volume, as you go to fainter magnitudes, then you're looking at larger distances, and you enclose more stars in your volume. Now that slope is also the exact slope at which you actually improve your astrometric precision as the number of stars increases such that your astrometric precision per logarithmic bin in V is equal up until that break. So your stars are getting fainter, but you're increasing the number of stars to exactly counteract the decrease in astrometric uncertainty per star. Okay, so basically, you get uniform contributions per delta V from the bright end all the way to this break. And then below that break, you basically don't get very much information at all because your astrometric precision of those reference stars goes down, but you don't increase the number of reference stars in a way that compensates for it. So you can think of basically the astrometric precision as just the effective number of reference stars brighter than this break magnitude. Okay, and so you can do this for different lines of sight, and you find basically you find surface densities in the plane that are of order 20,000 stars per square degree. You find surface densities that are near the galactic poles that are of order 100 per square degree. So your number of reference stars varies dramatically in a given field of view, depending on where you're looking. That's going to have important implications for your ability to measure. Okay, so so this is actually what I said in words before, but basically the bottom line is with a field of view of two arc minutes by 3 arc minutes, which is sort of the nominal field of view of the high resolution imager, you're gonna, in the galactic plane, you'll have enough reference stars, but near the poles, you're gonna not really have enough reference stars. So this pushes you to want to increase the area of the detector of the high resolution imager in HWO, and that itself poses challenges. But something like 10 times bigger detector would give you enough reference stars in all lines of sight to be able to measure the masses of Earths around sunlight. It requires a many gigapixel camera, just for reference. Okay. I actually don't know what time is it? Okay, good. All right, so I just want to, so I put this up because Aki likes scaling relations, and eventually we're going to be working in this into a science definition document, which will help define the hardware of HWO, assuming that this is a driving science goal. And so you can write down the signal to noise with which you can detect an Earth-like planet as a function of all the relevant parameters. And what you end up finding is, and I just want to spend a little bit of time on this, what you end up finding is that the signal to noise goes as the diameter to the -1 power. So if you double the diameter, you increase your signal to the signal to noise goes as the diameter to 1 power. So if you double your diameter, you double the signal to noise. Where does that diameter, where does that scaling come from? Well, I already mentioned that your astrometric uncertainty as a function of diameter goes as the diameter squared, 1 over the diameter squared, 1 power because your PSF gets sharper as you go to larger diameter, and 1 power just because your collecting area increases as the diameter squared, and therefore your photon noise goes as the square root of that. But you lose 1 factor of the diameter because for a fixed size of your detector, physical size of your detector in, say, centimeters, and a fixed F number of your telescope, a larger telescope has a smaller field of view on the sky and therefore has a smaller number of stars. So if your F number and your physical size of your detector is fixed, then you lose another power of the diameter. And that, again, is what pushes you to wanting larger fields of view in HWO for this particular science. All the other scalings are basically what you'd expect. They go as the exposure time to the square root of the exposure time, the typical magnitude of reference stars to the -0.2, 10 to the -0.2 times the typical magnitude, et cetera. You can also do this by scaling by a fixed number of pixels in your detector. So rather than keep your the physical size of your detector fixed, you want to keep the number of pixels fixed. That changes the scaling because if you're Nyquist sampled as you go to larger diameters, and you have a fixed number of pixels, you get to a smaller field of view. The net result is you get the same scaling with diameter, but the dependence on wavelength cancels out, which is kind of nifty. And that's just because as you go to smaller wavelengths, you get sharper PSF, so that's better, but you get smaller fields of view to be Nyquist sampled at a fixed number of pixels, and that means that you have a smaller field of view and fewer reference stars. So all that works out. So all of these scalings can be put into some sort of DRM-like machinery, and that's kind of what I'm planning on working on for the next few months and beyond the rest of my time here. Okay, so I just want to briefly segue into measuring the masses of the target stars. So this is a kind of nifty result, or nifty application of high precision astrometry with HWO. that hasn't gotten as much attention as measuring masses of planets. The basic idea is that if you have a star, a foreground star that goes by a background star, the foreground star's gravity is going to deflect the light from the background star. So this is the same thing that Eddington used to measure the general relativistic shift of background stars during a solar eclipse in 1918, I think it was, in order to prove that general relativity was correct, or at least the scaling of general relativity was correct. Same idea. This is called astrometric microlensing by some people, and it's been shown to work. So Kailash Sahu used HST to measure the astrometric shift of a background star due to a foreground white dwarf as it passed by, and you can see the astrometric deflection of the background star, which is directly proportional to the mass of the white dwarf. So able to measure the mass of an isolated white dwarf using just gravity, which is pretty nifty. You can use the same principle here. So we're going to have these reference stars, and they're going to be deflected as the foreground star moves by. So you just imagine a foreground star moving relative to the background stars. All these little background stars are going to trace out little circles due to the astrometric deflection. The size of those circles is going to be proportional to the Einstein ring radius squared, which is just a function of the mass and the parallax of the star, divided by the angular separation between the foreground star and the reference star. So the typical shifts here are going to be of order 8 microarc seconds, which is enormous compared to the 0.3 microarc seconds we're talking about for the reflex motion of the Earth, of the Earth-like planet orbiting it. And so we'll detect this astrometric shift with a typical signal to noise of about 800, and so the uncertainty on the mass will be of order 0.1% by measuring this astrometric shift. So I think this is pretty nifty. We'll be able to measure the masses of all of our target stars to better than 1%, just again using gravity. And so, of course, the uncertainty in the mass of the star translates directly into the uncertainty in the mass of the planet as well, because we're measuring the reflex motion of the planet and the star due to the planet. Okay, some practical considerations. First thing is, you might be thinking, okay, there's a 5th magnitude star here, and we're looking at 15th magnitude background and reference stars. Right? Isn't the light from the 5th magnitude star going to overwhelm the halo of the light from the star? Going to overwhelm the background, the light from the reference stars? And this is, of course, the problem that we're trying to solve with our 10 to the minus 10 contrast with the coronagraph. The thing is that in that case, we're trying to do it at 0.1 arc seconds rather than an arc minute. And so the Airy disk falls off as the angular diameter, the angular separation from the star to the -3 power. And so at a typical distance of your reference stars of about 1 arc minute, the flux due to the flux in the halo due to your target star is about 10 to the -11. So it's completely negligible. 10 to the -11 of the flux of the star, so it's completely negligible for these purposes. So this is not going to be an issue. There may be other issues, but this is probably not one. Another interesting thing to think about, which I think deserves a little bit of work, is that we're going to get orbits of these planets by going back and measuring multi-epoch direct images, and of course the orbits are going to be important to place the properties of the planet in context. And we're only going to know a planet is in the habitable zone by measuring its orbit. And so people have done simulations. So this is simulations by Eric Nielsen. This is from the HABEX final report, showing that for an Earth-like planet at you can get the astrometric, you can get the orbit to sort of semi-major axis and inclination of the orbit to sort of 10% with about 3 direct imaging measurements that are well spaced along the orbit. That's if it's 0 eccentricity. It's a higher eccentricity, then you require more epochs. But anyway, with a handful of epochs, the bottom line is you should be able to get orbits, at least of those planets that you can sample well over the course of their period during the duration of the mission. And so that means that you're going to know where the planet is, more or less, relative to the star, which means that you know which direction the astrometric shift of the planet due to the star due to the planet is, which direction it is, and the only thing you're fitting for is the amplitude. And that should help you with controlling systematic errors, because if your astrometric shift is in the opposite direction of what you expect, that's likely telling you that there's a systematic error or maybe some other object in the system that you haven't detected, and so that'll help distinguish between false positives and true astrometric. And the only free parameter you get is the amplitude of the signal, which is again directly proportional to planet mass. Okay, so right now the HWO is going through these exploratory analytic cases, which are these kinds of the notional mission concept designs that are being worked through to work on end-to-end modeling, identify key technology gaps, et cetera. And so as part of this, we're looking at different hardware requirements. And so the instrument you can imagine doing this with is the high-resolution imager, or maybe one of the guide cameras. The notional high-resolution imager properties has a UV, visible, and near IR channel. The band pass is between 200 nanometers and 2.5 microns. And the field of view notionally is 2 arc minutes by 3 arc minutes. Again, as I said, that might be a little small for the purposes of what we need. And then it has, arbitrary number of filters and dispersers. And exactly what filters would be best is unknown. So this is just, I won't go into this because I'm not a person that builds instruments or understands instruments, but there are designs for what this high-resolution imager might look like. And I'm currently working with Brian Starsky about ideas for how bad the distortion of the PSFs might get if you would just increase the size of the detector, keeping everything else fixed. That, of course, comes with the cost of increasing the number of pixels and the physical size of the instrument, but those might be manageable. And notionally, the camera design is 300 megapixels. So that's a lot, but that's not any more than Roman. Roman is roughly 300. All right, so I'm running out of time. So there's lots of questions. Again, this is very much work in progress, so, it's a little bit, lots of things to think about. One is, a question for the people that do the atmospheres, is how well do we need to know to measure the mass of the planets? And particularly for multi-planet systems, 10% seems doable. 1% is going to be really challenging, except for the largest planets. How well do we know the orbits? Can we use this to reduce the amount of time to get masses? What's the best observing strategy? How much total time is needed? Is it a significant fraction of the nominal mission lifetime? What wavelengths are best? Do we want a broad white light filter, which might induce chromatic issues with chromaticity? Or do we want narrower filters? If we want narrower filters, do we want a bluer filter where our PSF is sharper, but our reference stars emit fewer photons? And a redder filter where our PSF is fatter, but the reference stars are brighter. Can we use the guide camera for this, which nominally might have a larger field of view? Can we make the field of view of the HRI bigger without incurring too much degradation due to the distortions of the PSFs? How do we calibrate the detector, right? So we need to know exactly where a certain photon landing on the detector corresponds to about 2 times 10 to the minus 6 of a pixel. How do we calibrate detectors at that level? And then finally, we have a dynamic range issue. We have a 5th magnitude star sitting next to magnitude reference stars. So we have a 10 to the 4th dynamic range issue. How do we measure astrometry of that 5th magnitude star at the same time as measuring the astrometry of the 15th magnitude stars that we're referencing? So with that, I will end and take questions. Lots of chat, and hopefully they could actually hear us.
Yes, I think so. Awesome talk, Scott. Thank you so much. Yeah, we have time for a few questions. I saw David Bennett had his hand up earlier. So David, are you still there?
Yeah, so I had a couple questions related. So I didn't see any discussion of the amount, the exposure time used to make these astrometric measurements. Presumably, more exposure time gives you better precision. And then also, a few years back, I recall suggestions that the astrometry could be improved for, direct imaging systems by putting spots on the primary mirror to generate basically diffraction features that can improve your astrometric signal. Have you considered any of that stuff?
So in terms of exposure time, I think that's a really good point, Dave. In principle, we can do better by just exposing longer. The total amount of time notionally is I was doing 300-second exposures, which we'd probably want to do longer exposures than that, just because of the overhead of moving to the target. I think the exposure times are reasonable, but I think that's something that we want to look into. In terms of the diffractive pupil concept, this is an idea that I first heard of by Eduardo Bendick. This is just a slide he gave me. I don't pretend to understand the slide, but the basic idea is, again, you put spots. Doesn't necessarily have to be on your primary mirror. It can also be on a downstream optic. That gives you these diffraction sort of spikes, which you can measure the astrometry relative to those. That helps you calibrate the distortion of the detector, but could also help with your dynamic range issue. So that's something that I think is very promising. But I don't have anything intelligent to say about it other than that.
Great. I see a few more questions online, but let me just check in the room first. Anyone in the room want to ask Scott anything? All right. Carl, go ahead.
Hey, Scott. Can you hear me?
Yep.
I wanted to add something to your list of questions. You mentioned the stability situation for RV in terms of instruments. What is the stability requirement on the telescope to do astrometry at this level of precision, both, in terms of the PSF shape and then for the field distortion? How stable does that need to be?
So it's a good question, Carl. The answer is I don't know. Brianna and I started thinking about ways in which we could try to quantify that, how we can flow down from the requirements of the chronograph, the stability requirements of the chronograph to those, to then translate those into how stable the PSF is over time. And so I think that's a really good point, and something worth looking into. I would just say that part of the reason we've gone down this rabbit hole in the first place is because if you have a 10 or picometer or 10 picometer stable telescope, it seems like that would be a pretty good platform to be able to do high precision astrometry at this level. But quantitatively, I don't have the answer, and we're working on it.
Yeah, a lot of that stability might be in the coronagraph channel where there's dynamic correction. It might not be there for the wide field camera.
Yep, that's a great point.
All right, there's a question in chat asking how much do we have to worry about previously unknown astrometric motion of the reference stars?
Yeah, that's a great question, and I haven't thought about this very carefully, except to figure out how to answer that question. So yeah, the background stars will have proper motions and parallaxes themselves. These will have been measured by Gaia, but not at the precision we need in order to get the sub-microarcsecond astrometry. My hope is that if you have enough reference stars, then you can basically measure the proper motion and parallax with the data themselves and take it out. But on my to-do list is to work with the graduate student I mentioned, Kaz Gary, to do simulations of that to see how much additional noise that introduces into the astrometric shift of the target star.
Great. Well, we are at our time, so I think Scott's going to be around for a few more months. Is that right, Goddard? So if anyone has any other questions for Scott, definitely get in touch. But let's thank him again for a great talk. And thanks, everyone, for coming out today in the call.
Thank you.